All right, so let's get to the real focus of equation solving. And the real reason that we spend so much time trying to solve equations is that we actually want to solve inequalities. And this is actually a much more useful thing. We don't want to schedule our life so that we make exactly equal to $100,000 a year. We may want to schedule our life so that we make more than $100,000 a year. So here's a general approach to solving inequalities. What we can do is we can begin by looking for what are called the critical values. And these critical values will fall into one of two categories. They'll either be values of the variable that are absolutely forbidden because of the constraints of the arithmetic operations we're doing. Notably, this is dividing by 0 and similar operations. But we also have any solution to the corresponding equation. And what we can do with these is, at this point, these critical values are going to partition our number line into a number of intervals, each of these intervals is either part of the solution or it's not part of the solution. So what we'll do is we'll check each interval and we'll identify the ones that solve the inequality. For example, let's take a nice simple inequality, 5x minus 12 less than or equal to 23. All right, so I'll look at this expression, and whatever x is, I can multiply it by 5, no problem. I can then subtract 12, no problem. So any value of x is allowable here. There are no forbidden values, so we'll begin by solving the associated equation. And that's going to be almost the same statement, but I'll replace that less than or equal to, that inequality, with an equality. So that's 5x minus 12 equals 23, and I solve this using our standard methods, and I get x equals 7 as our solution. And so now that gives us our one critical point, x equals 7. We'll plot that critical point. We'll set down a number line, locate 7, and because the inequality is a less than or equal to, that less than or equal to actually allows us to have equality, we'll go ahead and use a solid circle at x equals 7. And that x equals 7, no matter what, will be part of our solution set. And here's the important thing to notice. If we view this as a boundary, we've separated our number line into two intervals. We have the stuff to the left, and we have the stuff to the right. So I'll pick a point in each interval. How about something to the left of 7? Well, how about 0? And something to the right of 7? How about 1 trillion? And here's the thing. It really doesn't matter what this value is, 1 trillion or 0 or whatever, as long as they're in the correct intervals. The only requirement is ultimately we're going to have to check to see if they satisfy the inequality. So let's check this out. Our test point x equals 0, I'll see if 0 satisfies the inequality. So if x is 0, I'll check it out. X is 0, that's going to be negative 12. Is it true that negative 12 is less than or equal to 23? So, well, it's a true statement. So that means that 0 is part of the solution. I'll go ahead and fill that in. And also any part of the interval that contains 0 is also going to be part of the solution. And that interval, the only boundary is right here. So it's going to include everything up to 7 and everything over to the left. So I'll shade that in. Now, what about the other side? So we'll check our other test point at 1 trillion. And here's the reason I used 1 trillion. So it won't be part of the solution, and we don't have to compute with that. We can just reason our way through it. 5 times 1 trillion is a whole lot. Minus 12, certainly not going to be less than or equal to 23. So 1 trillion is not part of the solution, and despite popular sayings, it's not actually part of the problem either. It's just not part of the solution, so we don't mark it, and our solution graphically is going to look like this. Now, we do want to answer questions in the same dialect they were given in. So here our question was asked in terms of an algebraic statement. This is a geometric picture of our solution. So we do want to translate this geometric picture into an algebraic solution. And so notice here we have everything that's less than or possibly equal to 7. So I can write my solution as x less than or equal to 7. Or the other possibility, if we use interval notation, again, not really the best way of expressing solutions, but I can express it this way. X is going to be in the interval minus infinity not included, all the way up to 7 do include that endpoint. All right, let's take a look at another problem. Solve 3x minus 5 over x plus 1 greater than 5. A little bit of analysis goes a long way. Over on the left-hand side, remember the fraction bar is a grouping symbol. Do the stuff up top, do the stuff on the bottom, then divide. I have a quotient over on the left-hand side, and because it's a quotient, I cannot let the denominator be 0, which means I have a critical point anytime I have something that'll make the denominator 0. So I have x plus 1 equal to 0. If x equals negative 1, I have a problem. If x equals negative 1, the denominator is 0. That's a bad thing. We have to avoid it. So x equals negative 1 is a critical point. The other critical points come from actually solving the equation. So I have 3x minus 5 over x plus 1. And again, this is a quotient. We are dividing by something, so I can undo that by multiplying by whatever we divided by. So we're dividing by x plus 1, so I'll multiply both sides by x plus 1. I'll do a little bit of algebra, and I have this. And let's see, so I have a subtraction addition, and I can solve that. I'll get everything onto one side. That's 3x minus 10. And let's see, I'll subtract 3x, that's 2x equals negative 10, and multiply x is equal to negative 5. And there's my other critical point. All right, so I have the two critical points. They're either the things that are going to make the expression undefined, the forbidden values, or they're things that are going to make the equation 3x minus 5 over x plus 1 equal to 5. So let's go ahead and plot those on the number line. So I have a point at negative 5. I have a point at negative 1. And because the inequality is a strictly greater than, not allowed to be equal to, I do want to mark the critical points with open circles to indicate that they will not be part of the solution set. All right, so now let's take a look at this. I have two critical points. I have 1, 2, 3 intervals that I've partitioned the real number line into. So I'm going to pick a point in each of those 3 intervals. So for example, I might pick in this interval 0, in this interval, how about like negative 2 maybe, and in this interval, how about negative 10 or something like that. So I can pick a point in each of those intervals, and I'll test each point. So I'll check x equals 0, and I'll substitute that into my inequality and see if I get a true statement. So letting x be 0, I simplify this negative 5. Is it greater than 5? And I think about that for a minute, and I realize, no, this is not a true statement. 0 is not part of the solution, so we do not shade the section that includes 0. Well, our next test point, x equals negative 2. Again, I'll substitute that into my inequality and see if I get a true statement. So let's see, all the dust settles, 11, and 11 is greater than 5. It is true that 11 is greater than 5. So x equals negative 2 should be part of the solution set, so I'll go ahead and indicate that. And I want to shade the interval that includes negative 2, and that's going to be this entire middle section. Then x equals negative 10, same sort of problem. If I let x equal negative 10 in my inequality, I can see if I get a true statement. So what do I have? I have this. I calculate it, and it is not true that negative 35 over 11 is greater than 5. So it's not true. X equals negative 10 is not part of the solution set, and I don't want to shade that section. So again, this is a graphical view of the solution. I do want to translate that into an algebraic form, and I'll note that I'm looking at everything x that is between negative 5 and negative 1, and I'm not going to include either of those endpoints. And again, if I want to write this in interval notation, that's going to say x is something that is from larger than negative 5 up to negative 1, but parentheses say don't include either one of those.